Hi everyone, welcome to the fifth and final installment in our Object-Orientated Programming series. Today we will be looking at the concept of polymorphism. Object-Orientated Programming is of course when programs are written in terms of objects and classes, and this differs from procedural or functional programming, where programs are written as a series of functions, or sometimes termed modules. Previously we learned that objects are unordered collections of properties, meaning data, variables, sometimes termed fields, and methods, by which we mean functions. Therefore, properties are things an object has, for example, name, age, height, and weight, whilst methods are things an object can do, for example, walk, run, swim, fly, and so on. We also learned that we can create blueprints for objects called classes, and that objects can therefore be instances of a class. And when an object is created as an instance of a class, it is said to have been instantiated. As an example of objects and classes, Lassie is an instance of the dog class. There are many dogs, but there is only one Lassie, and this is the correct relationship between objects and classes. Much of this was covered in much broader detail in the first video in this series, and I would suggest you go back and take a look at that video again if you don't feel comfortable with these concepts. For this video, we will also be making use of the concepts of inheritance and encapsulation. We will recap on these subjects as we go, but again, if you're unsure, take a look at the second video in this series for inheritance and the fourth video in this series for encapsulation. So if you're good and you feel comfortable with these concepts, we will move on and look at polymorphism. Polymorphism comes from the word poly, meaning many, and morph, meaning form. Form is the outward appearance of something, and in this context we are concerned with the outward appearance of objects, or how objects interact with external code, meaning code outside the class declaration for that object. This is also called the object's interface. In this diagram I have a me object with the properties first name and last name, and the method walk. Next to the object I have my pseudocode showing how I would access the members of the object externally, i.e. using code out with the class declaration for the me object. Notice that because it is possible to encapsulate members of the me object, there is not always a one-to-one correlation between the interface of the object and its structure. This is because when members of an object are encapsulated, or we could say hidden or made private, they can no longer be accessed by external code. This means that the first two lines of pseudocode won't work, and we have therefore altered the object's interface by using encapsulation. Polymorphism is in a sense poorly named, as it is not about objects having different interfaces, but rather the same interface, despite being instances of different classes. This means having objects which are of different classes, but which have the same interface. Let's take a look at an example program written in pseudocode which suffers from a lack of polymorphism. This example program is designed to display a shape onto the screen. The shape should either be a circle or a square, and it should be random which one we get. First we have our class declarations for the circle and square classes. The circle class has the properties radius and color, as well as the method draw, and the square class has the properties height, width, color, and the method display. We can see that in these class declarations, each of the properties has a preset value, so this will be the value of these properties for all objects which are instances of these classes at the point of instantiation, or at the point when they are created. For this program, we also need a getARandomShape function, which gets a random number between 1 and 10, then returns a new instance of the square class if the number is less than 5, and a new instance of the circle class if it is not. Finally, we have our main statement. We have a boolean isFinished variable set to false, and we say whilst the isFinished variable is equal to false, we want to create an object, shape, which we will set equal to the return value of the getRandomShape function. This means each time this loop is run, the shape variable will either be an instance of the square class or an instance of the circle class. We then call the method draw, which is a member of the shape object. Notice that underneath I've put in comments that this will only work half the time, because half the time the shape object will be a circle, which has a draw method, and the other half of the time the shape object will be a square, which does not have a draw method. When the shape object is a square and we attempt to access the draw method, we will be attempting to access a method that doesn't exist. The draw and display methods in our example will do slightly different things, because the process of drawing a square to the screen will be different to the process for drawing a circle to the screen. However, this difference is not relevant to the external code. In our main statement, we do not want to be concerned with what type of shape we have. We just want the quickest and easiest way to tell the shape to draw itself. Here's a possible solution to the problem. We have updated the main statement, which would make use of an isInstanceOf function to test whether the object shape is an instance of the circle class. IsInstanceOf is just pseudocode. How exactly you would test what class an object is a member of would vary quite a bit from one language to the other. We test whether the shape object is an instance of the circle class, and if it is, we call the draw method, and if it is not, we know it must be an instance of the square class, and we call the display method. This solution means we have to test what type of object it is we want to draw or display. This is excess code which is unnecessary. It also means the code is inside our main statement, which is not where we want it to be. The logic in our main statement is that we want to create a circle or a square at random and draw it to the screen. We only want the bare minimum of code necessary to achieve this in our main statement. The simplest and most obvious solution to this problem is to rename the display method to draw, so that both classes have a draw method, and this allows us to remove this excess unwanted code. Here's our updated class declarations illustrating this. You can see that both methods are now called draw. Our getRandomShape function remains the same, and our main statement is back to the way it was originally. And I've removed the comment because we now know this will always work. Regardless of whether the shape object is a circle or a square, it will always have a draw method. We could now say that we have made the classes more polymorphic with one another because there is now a greater similarity between the interfaces of the objects which are instances of these classes. This means that we can implement a form of polymorphism by using some standard for the names of our methods. Now we will look at achieving polymorphism through inheritance. Previously, we learned that classes can inherit members from other classes, and we learned that this is often done through the extend keyword, which is a keyword common to many programming languages. We also learned that it is appropriate to use inheritance when the inheriting class, often termed the subclass, is a more specific version of its superclass, or the class from which it is inheriting from. As an example of inheritance, we could have a Honda class be a subclass of the car class, and we would therefore say the car class is the superclass of the Honda class. A Honda is a car, just a more specific description of an object than car. A Honda is not a discrete individual object because there are still many Hondas and there are still many cars. All Hondas are cars, but not all cars are Hondas. And this is the correct relationship between subclasses and superclasses. Let's take a look at what our shape drawing program might look like if we used inheritance. We have a shape class with the property color and the method draw, and we have our circle and square classes which inherit from or extend over the shape class. The square class has the properties height and width, whilst the circle class has the property radius. If we look at our program so far in diagram form, we can see that instances of the circle and the square classes will have a color property and a draw method inherited from the shape class. If we take a look at the draw method of the shape class, we can see that in this method we check whether the object which has called the method is an instance of the circle class, and if it is, we do whatever we need to do to draw a circle to the screen, and if it isn't, we do whatever we need to do to draw a square to the screen. This means that the circle and the square classes are polymorphic to the same degree as in the previous example, but not because we adopted a standard for our method names, but rather because we used inheritance to enforce the polymorphism. Finally, we'll look at using the concept of encapsulation to enforce polymorphism. This diagram shows circle and square objects. Each has the method draw and the property color, but the circle has the radius property, whereas the square has the width and height properties. If we encapsulate the radius property of the circle class and the height and width properties of the square class, attempts to access these properties via external code will fail. This means that as far as external code is concerned, objects which are either circles or squares can be treated the same. They are now completely polymorphic with one another. They have different structures, but they have the same interface. Remember also that by encapsulating these members, we are not preventing the draw method from having access to them, as the code for the draw method is part of a class declaration and is not external code. In conclusion, we have learned that to make classes polymorphic means to give them a common interface. This increases the modularity of external code. Modularity is a term in computer science to describe something which is easy to use in a wide variety of circumstances and has been deliberately designed to be so. In our example, when we implemented polymorphism on our circle and square classes, we made the code for our main statement easier and simpler than it was when we tried to solve the problem without polymorphism. We've learned a few different ways to implement polymorphism. We've learned that we can implement polymorphism using standards for our method names, and that we can use inheritance, encapsulation, or a mixture of both to implement polymorphism in our code. And that concludes the final tutorial in this series. As always, rate, comment, subscribe, post me some feedback and let me know if this tutorial helped you, let me know if you learned something. Stay tuned for more tutorials, and I look forward and hope to see you there.